Hello, my name is Blake Smerigan. I hope that you are doing well. Today I'm going to be discussing the results for a quick startup procedure for a decentralized high-strength wastewater treatment system. I conducted this research along with Benjamin Thomas, Sibel Uladag Demir, Douglas Clements, Henry Frost, and Wei Liao. The main goal of this research was to establish a decentralized wastewater treatment system that is capable of handling high-strength wastewater called black water. One objective we had to accomplish this goal was to devise and test a quick startup strategy for a compact baffled bioreactor that is able to purify the black water in less than the 45 to 60 day period typically needed to reach desired purity. Another objective we had was to find the ideal amount of carbon and nitrogen to add in a shock dose to shorten the startup time. Finally, we wanted to test the removal of the major pollutants in the water over a 7-week period to see the effects of the dose on the purity of the water. Shown here is the location of our testing facility. We wanted to be able to prepare the wastewater for the bioreactor to help prevent any malfunctions in the system. We did this by having the sewage be first pumped into a sewage buffer tank and then transferred to the clarifier with the activated sludge. After this, it was pumped to a mixing tank before finally being pumped to the bioreactor for testing. Here is the flowchart for the black water preparation. The sewage was obtained from the East Lansing sewage system. This was then pumped using a grinder sump pump to the buffer tank. The sewage in the buffer tank was then pumped using a regular sump pump to be mixed with the activated sludge. This mixture was then pumped with a diaphragm pump to the mixer. Once thoroughly mixed, the influent was pumped to the treatment units to begin its purification. We ran 2 startups with this system. Both startups were conducted with a 1,400-gallon aeration tank. The first startup was conducted with the addition of 5 kilograms of table sugar to act as our shock carbon, as well as half a kilogram of fertilizer to act as our shock nitrogen and phosphorus. The second startup was conducted with higher amounts of our shock nutrients. We added 20 kilograms of the table sugar and 1 kilogram of the fertilizer for this startup. For both startups, we measured the effluent before and after adding the shock dose, as well as 3, 6, 10, 24, 33, and 48 hours after the initial addition. As seen in the charts, the first startup did not have a significant increase in pollutants after the shock dose was added. This meant that the shock dose did an insufficient job at initiating the nitrification and denitrification needed for nitrogen removal, as well as initiating the carbonaceous organics of the activated sludge. The second startup had a significant increase in the nitrification and carbonaceous organics. As seen in the total solid COD and TOC charts, at about 6 hours, the peak pollutant value was reached and the values began to descend back to their pre-shock dose values. For TOC in the second startup, we did not take values at the 3 and 10 hour mark. These patterns were also seen in the TKN, ammonia, turbidity, and total phosphorus values. Startup 1 has a relatively flat trend line which illustrates its lack of speed up from the shock dose. For TKN and ammonia in Startup 2, a steep decline in pollutants was seen after the 6 hour mark. The total phosphorus was not seen to have a strong decrease in the first 48 hours after the shock dose. The turbidity of the water also seemed to not be heavily affected after 48 hours. Over the course of the 7 weeks that we tested the purity of the water after Startup 2, we found that there were significant decreases in the amount of pollutants in the water. We tested the influent effluent each day to see the efficiency of the system. The total solids and total suspended solids continue to have a fairly linear change, with only a peak seen in week 3 for total solids, most likely due to a change in influent composition that occurred. In about the 2 to 3 week period, the results began to match the 45 to 60 day results using standard startup procedures. This consistent purification is particularly obvious in week 6, where there was a large increase in pollutants in the influent while the effluent was relatively unaffected. Similar to the initial kinetics, these trends were also apparent in the TKN, ammonia, BOD5, and total phosphorus weekly averages. TKN and ammonia had consistent decreases in pollutants over the 7-week period. BOD5 had a peak in week 4, but was consistently low through the rest of the weeks. Total phosphorus had a fairly consistent decrease, with slight increases that corresponded to the increase in the influent levels. The conclusions we were able to obtain from the results were that the startup period for the nitrification and aerobic biological treatment can be shortened by adding a shock dose of carbon and nitrogen. We found that after 15 to 20 days, the startup purity was below the criteria of 45 milligrams per liter for a 7-day average of BOD5 and total suspended solids, as well as meeting the criteria of a pH of 6 to 9. This was significantly faster than the 45 to 60 day startup time it typically took to achieve these criteria. In 15 to 20 days, we were able to achieve a 33 milligram per liter average of both BOD5 and total suspended solids, while also achieving only 26 milligrams per liter of oxygen. Also, we found that there was a change in the influent composition during week 3 due to changes in the population dynamics caused by COVID-19 adjusted actions in East Lansing. I would like to thank Yan Liu and James Dusenberry for their help in this research, as it would not have been possible without them. I also want to thank the Department of Defense for supporting this project. Thank you for listening to my presentation. I hope that the rest of your day goes well.